All right, let's jump right in. Today we're telling a story. It's a story of science, of rebirth, and of the invisible heroes that are literally holding our cities together. We are going deep into the world of structural engineering to figure out how a new generation of super fibers is bringing our aging infrastructure back from the absolute brink.
Just think about that for a second. What if you could bring a dying bridge back to life? Not just tear it down and start all over, but actually resurrect it. Well, this is the massive question that's driving a whole new field of engineering. It's turning experts into a kind of structural detective, investigating clues left by time and stress to pull off some pretty modern miracles.
So you gotta understand, when a structural engineer looks at a crumbling bridge or a cracked support pillar, they're not just seeing decay. To them, this is an active scene. They aren't just identifying a problem, they're actually finding an opportunity to jump in and completely rewrite that structure's future.
And that right there, that's the key mindset shift. For decades, the only answer was demolition, just tear it down. But now it's all about sophisticated repair, which is a total game changer for our cities. It's cheaper, it's faster, and hey, it preserves our history. The secret weapon in all of this? These advanced materials called fiber-reinforced polymers, or FRPs. Think of them like a high-tech exoskeleton for concrete and steel. Okay, so every good detective needs a toolkit, right? Well, a structural detective is absolutely no different. They have 5 core techniques they can use to bring a structure back from the dead. So let's take a look and see what's in their bag.
Let's just quickly run through the core techniques here. First, there's section enlargement, and yeah, it's exactly what it sounds like. You just make a column or a beam bigger so it can handle more weight. Then you've got grouting, where engineers inject these special fillers to seal up cracks and restore integrity. And post-tensioning is this really clever technique where they add new internal cables to actively squeeze the concrete, fighting back against the forces trying to pull it apart. These methods, often used with advanced composites, like those FRPs, are pretty much the foundation of modern structural repair.
And for a specific problem, let's say a failing beam, the detective has to make a choice. Do they cut grooves and embed the FRP bars right into the concrete? That's called near-surface mounting, and it gives you incredible, long-lasting protection. Or, hey, maybe speed is the most critical thing. In that case, do they bond FRP plates right onto the surface for a super-fast boost in strength? Every method has its purpose.
So, what is it that makes these materials so ridiculously strong? I mean, at the end of the day, they're basically just fibers, held together by a kind of resin. To really get the secret, we have to leave the construction site for a minute and step inside the forensic lab to look at the material's DNA.
The secret is a science called micromechanics, and it's all about understanding the relationship between the 2 key ingredients. You've got the incredibly strong fibers that do all the work, and then you have the polymer matrix that holds them in place and protects them. This science lets you predict the strength of the final material before you even make it. Pretty cool, right? And right at the heart of micromechanics is this core principle, the rule of mixture. Think of it as the mathematical heartbeat of the whole operation. It basically says that the strength of the final composite is just a predictable blend of the strength of its parts. This is the secret code, the recipe that lets engineers design these materials with surgical precision. Okay, let's put it to the test with a real-world puzzle straight from the lab. You've got a composite material, and you know that 60% of its weight is from the glass fibers. But, weight isn't everything. The real question is, when you pull on this thing, who's actually doing all the heavy lifting? And this just brilliantly shows the answer. It's not even close. After you run the numbers, it turns out the fibers, which are less than half the volume, are carrying nearly 95% of the load. The matrix? It's really just along for the ride, holding everything together. This is the big so what moment. The fibers are the true workhorses here. Okay, so now that we understand the material's secret strength, let's head back out into the field. We're going to see how our structural detective applies this science across 3 critical battlegrounds. The first theater of war is bending, or flexure. By bonding an FRP plate to the bottom of a beam, you give it extra muscle to resist bending under a heavy load. But, and this is a huge but, there's a crucial trade-off. You gain immense strength, but the beam becomes more brittle. That means it could fail really suddenly, instead of sagging first to give you a warning. The second theater is shear. That's the force that creates those nasty diagonal cracks you sometimes see in a beam. The solution here is to wrap the beam in FRP, basically stitching the cracks shut. And the evidence on this is crystal clear. A U-shaped wrap that goes around the bottom and sides is way more effective than just sticking strips on the sides, simply because it anchors itself.
And finally, we've got axial strength for columns. Wrapping a column in FRP is kind of like giving it a high-tech corset. When the concrete tries to expand outwards under a heavy load, the wrap pushes back, making the column immensely stronger. But there's a hidden danger: sharp corners. They create these stress points that can cause the wrap to fail. Rounding those corners isn't just a good idea, it's absolutely essential.
And look, these aren't just theories. They're the result of decades of real forensic research. As you can see here, key findings built on each other. Back in '91, researchers proved the concept worked, but warned about these new peeling failures. By 2004, they had actually quantified the critical importance of rounding the corners. And by 2007, they had pinpointed the perfect fiber angles to resist shear cracks. Each discovery was a stepping stone to the techniques that are used today.
So after all the fieldwork, the lab analysis, and reviewing past cases, our structural detective files their final report. And this isn't just about one single repair. It's the blueprint for how we build and maintain a more resilient future.
But the material itself is only half the story. How you actually manufacture the parts is just as important. For a unique, custom job, you might use something flexible like contact molding. But for mass-produced, super high-strength beams, you'd use an automated process like pultrusion. Each method is a strategic trade-off between cost, speed, and precision. So in the end, it all comes together in a final checklist. The engineer has to analyze the structure's geometry, confirm the micromechanics of the composite, and pick the right manufacturing process. Crucially, they have to address all the details we talked about, like rounding corners and getting the fiber angle just right, and then carefully weigh that trade-off between raw strength and ductility, which is the structure's ability to bend before it breaks. Following this playbook is what makes a structural resurrection successful. So the next time you drive over a bridge or walk into an older building, just look a little closer. You might be looking at a silent giant that's been given a second chance at life. Our cities are like a library of lessons learned from concrete and steel. The real question is, what new stories are we going to write with the super materials of tomorrow?